Hey everybody, Blake here with another video on my series about spacetime particles, which is basically the quest to simplify physics using a medium that defines spacetime. And I'm hoping to show that we can get rid of a lot of the more uncertain theories out there using this medium. In this video, we're going to talk about how gravity does not bend light. That sounds pretty crazy, I know, at the moment, but by the end of this video, hopefully, it will be a little bit more reasonable sounding. Now this is a re-recording. I had to update some of the math, and I also made this video a little bit more detailed than my previous one. So, and I changed the format. So hopefully it will be better in every respect. But let's get started. The topics for this one is just going to be light in space-time. I don't know how we're going to be kind of bouncing around. We have some random tangents, and so I don't even know how to describe the topics for this one. But yeah, mostly just light in space-time. So the first question I always wondered is, does light bend space-time? Now, general relativity would say that photons are energy, so it should contribute to the stress energy tensor. So I guess, is that a yes? I don't know. Somebody that's an expert on general relativity can say so. And if it does bend space-time or create gravity on its own, does it emit gravitons? How does something moving at c emit something at c? So there's just some questions. But how I kind of like to resolve this in my mind is with this bagillion watt laser. Now, I'm pretty sure that's a technical term for a laser of unimaginable godlike properties. Okay, so we have a laser, my bagillion watt laser, and what we're going to do is this is going to send out a pulse of photons, maybe over 1 second. I don't know if it matters. But the energy here of this pulse is going to be equal to 1 mass of Earth mass. Yeah. And then the amount of energy involved in this is considerable, and so I want to do my experiment kind of far away. You're turning the amount of mass from Earth into pure energy, so that's going to cause some gravitational waves, maybe, I don't know. But we want to do this far enough away so it's smooth, and we're going to have a blue person over here. We're going to make this, the radius of the Earth, something that would be reasonable here. And when the photons here, is there a force of gravity? So I don't know. This is kind of how I would imagine an interesting thought experiment. So if we're looking at this photon or whatever it is, and it's moving at c, how is it distorting or, creating, emitting these photons or gravitons? Because we know that the relativistic aberration of light gets really nasty when things are moving at c. Basically, would that be kind of similar how you're going supersonic and there's some sort of shock wave and that, what is a graviton symbol? Graviton would be going out at that angle at c. I don't know. Anyway, so I tend to think that as this big lump of photons passes by the person, I don't think they would feel any substantial gravitational pull from this thing moving by. There might be like weird ripplings and stuff because that's such a huge amount of energy. But I personally, overall would say that photons do not create a gravitational effect. And maybe this is just me rambling here. But if anybody else has any ideas or good thoughts on this, that would be great to see in the comments. So, moving on. Okay, so now we're just going to look at the density of space-time and how that can influence everything. we're going to be looking at how properties change for different densities. And we're going to do the same thing Einstein said, is that light is always measured at c. Now I want to put an asterisk there because I don't think it's fair to say that this is this holds to all situations, to, any energy level, any density, anything. So I just want to say that for now, when gamma is relatively low and we're looking at, large scale events, not just particles, we can shoot particles really fast and they, behave as we'd expect, but relatively, in the grand scheme of things, that's low momentum. And so I just want to say that we're going to use this principle, but that principle is not going to necessarily apply to all energy ranges, all densities, because it's actually interesting if you allow physics to change with varying densities, then we actually simplify some other crazy things. So we'll get into that later. So anyway, so we have our standard. We're going to call this frame 0, n equals 1, and rho equals rho 0. We're going to call this frame 1, n equals n1, rho is greater than the standard. Now, what I'm going to say here, we're going to define some more. This is distance 1, 1, d0, 0. So d1 in frame 1. And we're going to define this principle or an equation. So d1 times n1 equals d11. Or if we're just looking at some, I don't know why that's that kind of x. And the result here would be that if n changes one dimensions, then the density is going to be proportional to the cube, because density is proportional to volume. But what does this mean? So if we have, d11, and we want to observe it in the 0 frame, it is going to look to be shorter. And that's what we get up here, right? So if n equals 2, d10 has to be half of d11. And that's kind of what we get there. Now, the speed of light we said is going to be constant for all frames. So we're going to say speed of light is equal to d divided by t. It's going to be equal to d00 divided by t00. And it's going to be equal to d11 divided by t11. And so we're interested in first, how does time flow in the different frames? Well, time is just equal to distance divided by c. And we're going to be looking at time, how, they compare to the different frames. So let's look at time 1 over some distance over some speed of light. Now, we don't know how the speed of light changes as observed from different frames, but I do know the speed of light of frame 1 in frame 1 is going to be c, right? Because we have c11 equals to d11 over t11 kind of thing. Now, we're going to want to cover a distance in our frame 1. And so we're going to be looking at a distance x1 in frame 1. But we want to look at how it looks as seen from frame 0. Now we have to do some adjustments here to make this comparison work. And so first we're going to get the distance into frame 0 units. Okay, so now what does x10 equal? That's going to be the distance of, some distance as observed from frame 0. And we want to do some related distance that makes sense that we know, like, so d over t in frame 0 is going to equal to c, so we'd like to get to that reference distance. Now what we're interested in this distance here. So we want to travel some distance that also equals x, or equals our standard d, right? So what does x10 have to be? What does x11 have to be such that x10 is equal to d? And that is basically what we get here. And so if we plug in d11, okay, so we get this, and then that means that t10 equals t11 and 1. And so as observed from frame 0 over a common distance, frame 1 is going to have to cover more distance, right? Because there's more of frame 1 compressed in the same area or length. And so it's going to take longer as observed from frame 0, right? So basically if 1 second passes in frame 1, then we have an n of 2, then frame 0 is going to observe 2 seconds passing, right? So frame 1 is going to observe to have slower rate of time. Now let's look at what does the speed of light look like in the different frames. So see the speed of light, so we're looking at the speed of light of frame 1 in frame 0, and we want it to cover some known distance, d00, but it's going to be the time, right? It's going to be t1, but as seen from frame 0. And so we just need to adjust that time the same. Right, so C10, I guess this could be 0, but basically as observed from another frame, light is going to be moving or appear to move slower, right? So if speed of light, if n equals 2, then speed of light observed from frame 0 is going to be half of the speed of light. Now you can also do, you can relate it to different frames through something like this. So what we said in the last one, or what we showed in the last slide, was that the speed of light doesn't always look to be traveling at c. Now, the reason why I want to bring this up is just because I tend to always fall for very literal traps. And when Einstein does his proof for special relativity, you'll see that he's measuring the speed of light in 2 different frames. And so then when I assumed that the speed of light was constant in every frame, you'd look down at like another planet or something very large, a massive body, and you would still see light moving at c. And this is just not the case, and I'm sure experts in general relativity are aware of this little trap, but I just want to make it clear for me and everybody else. So here we have this little diagram where we have some sort of black hole, and then set at an r equals to the photon sphere, the black hole, we have a laser. And the photon sphere is a place where if you fire light, it will orbit the black hole and return back to the same spot. And along this orbit, we're going to have little photon sphere stations. And every time they register a pulse of light from the laser, they'll notify some satellite or some receiving station that's very far away from the black hole. And this is, we kind of do this because we can't actually see the light down here, but we can signals of its path. Right, so basically we have S as the circumference of the at the photon sphere, and we're going to say the speed of light measured at frame 1, I guess we'll just say is going to be the circumference of frame 1 divided by time. And I believe that I'm not 100% on this, but I know that general relativity does distortions in the radial direction due to mass. And I don't think there's a distortion in the circumference direction, but if that's not the case, then please let me know in the comments. But so what we would know is that the time far away is going to be greater than the time close due to general relativity, the time dilation. And so we know that we can invert this inequality. And so as I showed before, the speed of light as observed from another frame, assuming that that's in a higher gravitational field, is going to show that the light does appear to move slower. But again, locally, you're always going to measure it at the same speed. So now we're going to do some tangents here, and we're going to look at time and materials. Okay, so one thing that is often done is that we say, as an observer, or as a an astronaut or whatever, a space person goes faster, their time goes slower and slower and slower. And then we say, well, and then it goes to 0 when they hit C, which is not possible because blah blah blah, whatever. The point though is that a photon is moving at C, and so it has 0 time flows relative to the photon. Well, the time dilation I'm arguing is related to moving mass. It does not apply to photons. The photon only cares about the dominant inertial sphere it is currently traveling through, so its frequency is actually tied to that frame. That frequency acts like a heartbeat and describes how it evolves over time. Right, so like if we do an experiment on a spacecraft between two distances, we're going to say, oh, that distance is 10 wavelengths apart. But then somebody else is going to look at that same experiment and they're going to say, oh, that is also 10 wavelengths apart. And so what I want to say is that the photon is going to move through space-time, and its time's going to flow, and it's kind of going to be relative to the heartbeat of that, of its frequency or wavelength, and relative to its frame. Whether this really matters or anything, it's just something I want to say because I feel like it's important. Now, why are we talking about light and materials? We'll get to that, a little bit of a tangent. But in modern physics, we have light coming into, some sort of material that with, maybe water, or, this could be air. And we're going to say that, or we observe that this is C, and we observe that this is velocity of the light over here is going to be c divided by n. And how we explain that is that we have a component of gamma going through at the same speed of light, whatever, but then there's some sort of response due to the electrons made up in, the electrons in the water, and that has some sort of response here. So maybe it's like a field response. And the grand total of the wave moving at c and the response of the electrons is anyway, that's what I think. I think that's the simplest, like it's a dumbed down explanation a little bit, but that's how modern physics would explain the decrease in the speed of light in different materials. Okay, so let's look at light in materials from the perspective of space-time particles. Light is just an oscillation through space-time particles, STPs. An electron is basically space-time particles in a different configuration or concentration, right? It could be a billion space-time particles collapsed into a higher concentration that gives off the properties of an electron with mass. Glass is just a lattice of atoms or molecules that fixes these electrons in place. A fixed grid of electrons is essentially a medium for light to travel with different properties of just vacuum space-time particles, right? So the properties of this medium could have higher densities. It could be, it could have different responses, but overall, all these different properties could inhibit the speed of light. There's other restrictions that this medium has, and that's, the electrons are tied to the atomic lattice. And so if you try to put too much energy into this medium, the medium is going to break, which causes an ejection of an electron from the lattice, right? And so electrons can only respond so fast. They can only carry photons of so much energy. And because of these restrictions, it's easy to see that electrons with mass can only respond so quickly. So maybe this would inhibit the speed of light due to different energy levels or different wavelengths. Space-time particles in a vacuum don't necessarily have these restrictions, so all wavelengths would travel at c. And again, I say in most normal cases because I don't know where we can extrapolate this to, and we just need to be careful. So all that to say that mass can increase the density of the space-time particles in the vicinity, and light bends because of this change in density of space-time particles, kind of similar to how it goes through materials. So let's look at what that looks like. So typical general relativity is going to describe space-time as being stretched. And so basically, if you have a large mass, it's going to stretch. This is just the kind of the rubber sheet analogy where the rubber sheet is stretched with a large lead ball or something. And so basically you're going to see space-time being stretched down towards the mass. If you were to be this little person here and you were to drop a rope down towards the center, the length of that rope is not going to equal the length or the radius that's observed from very far away. And so therefore you also have this situation where 2 pi length of the rope does not equal the circumference that you're at this location. And if you were to put little 1 meter sticks along the space-time, these little sticks are always going to be 1 meter. But as you observe from far away, this will be 1 meter here, but now you're going to see this distance can be much less than 1 meter. And so what does it mean for spacetime to be stretched? Well, let's look at another option. What if spacetime isn't stretched? It's just more of it is packed into a smaller location, right? So the density increases. So we do the same kind of thing. So as you move towards the mass, there's more and more density, or higher and higher density, and so there's more and more distance. And so these 1 meter sticks are going to be kind of have to travel more and more distance. So it's going to look from a far observer that distance is shrinking, which just so happens to be pretty much the same result as space-time being stretched. Now, if we're dealing with higher density, let's treat that density as if we're going from index of refraction, right? So if light comes in at an angle and transitions to a material with a different index of refraction, it's going to be turned towards this normal line. Now that's pretty extreme, maybe not accurate, but yeah, and so the same thing could happen with the density of space-time. So we have density is really high here, and maybe it's really low here. Right, so as this light ray is moving towards this higher density, it's going to be turned towards the mass, and then it's going to leave. So let's just kind of continue with this idea and see where it takes us. Okay, so we've got a couple things to look at, but in order to make this work, I'm going to propose something called the conservation of time. Right, and so I'm sorry, we're going to be talking about momentum, and we're going to be talking about period. And so a P like this is going to be period. Less defined P like that is going to be, and we're just going to be right in the beginning as this is the problem. But from before, we have the time. Right, so time as seen from the reference frame, 0, is going to be adjusted by the time in that frame by the index of, or n. Okay, so now let's look at the period. What does that look like for the period? So it's period. And so this is what I'm calling the conservation of time as light travels through from one index or one n to another n, or one density to another density. This needs to hold. And so let's just do this 1 over everything. And so if we do the inverse, we essentially get frequency 1, 0 equals frequency 1, 1. Okay. Now we're going to multiply okay, so that's equal to momentum. That's a P. That's a momentum P. So essentially, the momentum as seen from a higher, a lower density frame, reference frame, is going to be reduced by the density. So if P1 equals 1, you divide by 2, then the momentum is going to be half or whatever. And so one last thing we can do here for interest is we can say P1. Now, but let's also say that that is the same as P2, 0. And maybe that's just the same as P0. And P2, 0 would equal to, and so we can start to look at the ratios between, not necessarily just with respect to the reference frame 0, but between two different frames. that might not have a n of 1. Okay, so just super general, or just as a quick review or look-see, let's just say, if light starts in an area with a density of n equals 1 and it goes to n equals 2, that's momentum is going up, energy is going up, frequency is going up, but the period, maybe I should do this, is going down. And this is what we'd expect. As light approaches a larger mass, it's going to have more energy. The potential from very high is getting converted to energy of the photon. So that's nothing surprising here. One other thing to note, though, is that a green photon has the same energy regardless of density, right? So if you look at a green photon at n equals 1, that's going to be 1 energy. And if you look at a green photon at n equals 2, that's also going to be the same energy. And so how do we show that? Right, so the energy of the photon in frame 1 relative to the zero frame is going to be equal to this. These all cancel. So if and so right, and so that's just saying green photon always has the same energy, but a green photon traveling from different densities is not going to have the same energy or momentum. But anyway, so let's move on. Okay, so now, well, I am arguing that gravity is kind of, or at least not gravity, but the density of space-time kind of acts like the index of refraction. So we can do the Snell's gravitational law, which is something that I may or may not have made up. I'm sure somebody has thought about this before, so whatever. Right, so as light goes into N1, as light goes from, and we're just, I guess I'm drawing this as if N2 is larger than N1, but we can see that light comes in to this boundary with momentum of P1, and then it's going to exit with P2, and the angle is going to get a little steeper because I did say N2 is larger than N1. And then typically we have PX1 and then PX2. Right, and then from before P1 over N1 equals just this reference momentum. Right, so we have this, and we are going to, one of the common things when we're deriving Snell's law is that we say the momentum equals the parallel component of the light is equal or does not get changed. Then we could do some geometry. Px1 is equal to the momentum P1 times sine opposite over hypotenuse of theta 1. Px2, same thing, P2 sine theta 2. And then we, from above, Px1 equals Px2, we can then set these equal. P1 sine theta 1 equals P2. We can get rid of P2 with one of these with the relationship above. P2 equals P1 times N2 over N1. Okay. P1s can cancel, N1 comes over here, and we get Snell's law. N1 sine theta 1 equals N2 sine. Cool. Okay, well, let's confirm that this is correct. So basically what I thought is we're going to do the exact same experiment that Einstein did to validate general relativity. And that is saying that basically light coming from a distant star is going to just graze the sun. And if we have an eclipse and we can actually see this light, we can measure the apparent deflection of this light ray. And so we're going to try to predict that. And so we need to first understand how the density of space-time changes. So we're going to look at general relativity here. And general relativity says for a simple point source of mass, the time at a given r is going to be time far away and so basically if r is very big, then this goes to 0 and tr equals tf. So when r gets smaller, this is going to get closer to 1. And so we're going to perhaps say maybe 0.1 if we're very, at a very big m and a small r. So then 0.1 times time far away is going to be the time at that given location, right? So if 1 second passes far away times 0.1, then 0.1 seconds is going to pass at that given location. And we're going to here define a gamma function, r, and that's simply going to be t far away over tr, right? Because gamma is always greater than 1. Now, if we do that to the equation, we're going to have gamma r equals 1. And we're going to say gamma is proportional or equal to n. Now, when we do this potential, or I guess this density distribution or whatever we want to call it, I calculate 0.874 arc second deflection. Newton said the same thing pretty much. And it turns out Einstein originally said 0.87 arc seconds until he updated the equations, and unfortunately Einstein then predicted 1.75, and this was later verified. And so the correct answer is this one. So Snell's gravitational law, unfortunately, does not work. Well, the reason why things went wrong is because we said P1 of the parallel component equals P2 of the parallel component. Or I said P1. Right. This is not. I don't know. We're not necessarily allowed to assume that. And why this is not correct is because we did a right. So we said that the momentum changes because time is, the period is varying a little bit. But space-time varies in space and time. And so we need to account for that. How do we do that? Well, Fermat's principle is how we can really solve Snell's law, but we can do this with, space-time solution. And Fermat's principle is just saying that light will take the path that reduces the amount of time to get from point 1 to point 2. Alrighty, so we're going to now do this. Okay, so here is the general diagram for calculating the time, the least amount of time. We're going to start at point T1, and then we're going to take some path to the intersection point, and then we're going to arrive at P2 over here. And we want to figure out how we can adjust theta 1 and theta 2 such that we minimize time. And so if you imagine over here, right, so here's a plot of x1 versus time. If x1 is 0, that means that the light is going to come straight down here, and then it's going to take a really long path to point 2, and if n2 is larger, it's going to be very slow. So we'd expect, time when x1 equals 0 to be high. Now, alternatively, you could say that x1 is maxed out equals a, and so then light is going to take a path all the way just above P2, and then it's going to straight down. So here is we're minimizing the path length of N2, but we're making the overall path length way longer. So, that's going to be some sort of, here. And now if we vary in between, we're going to get kind of an equation like this. And so in order to find the least amount of time down here, we can take the derivative. The derivative is going to be equal to the slope of this curve. And so when the derivative is equal to 0, that's going to be equal to that point that we're interested in. And so typically how this is done, it's not just the paths that we're interested in, it's the geometry of the paths. So we need to have everything with respect to x1 so that we can do this derivative. I'm still calling this G2, but G2 is a minus x. It helps. And so basically what would happen is we would plug D1 into D1, plug D2 into D2, do the derivative with respect to x. The speed of light C1, 0 is going to be slowed down. C2 is going to be slowed down relative to the ends, and you can essentially calculate Snell's law. Right, so how we are going to do this is we're going to look at the path of light in a common frame, and that's going to still be T0 here, which I've done. But now this is not just D1, this is D1 in the frame 1's frame, because we're looking at the paths that light actually has to travel. This is D2 in the D2, or in the second frame. Right, so we're going to define this as G22. G2 is equal to a minus x1, still important later. X11 is the x in the one frame, h in the one frame. And so now we've set up the geometry to be reflected based off of the frame that we're going through. And what basically happens is now this is now D11, D22, right? So now when light is going from this path, it has a speed relative to n1, but it also has to cover distance relative to, the density as well. So when before it was just minimized, the angle was changing relative to the speed of light. Now it's changing because the path lengths are also varying. So if n2 is way bigger, it has to travel a lot more length. And so we almost get we get a double duty of trying to convert, turn the light towards P2. And so what we're going to do next is T0 D. Right, we're interested in the derivative of time with respect to the zero frame. And again, we're setting this equal to 0. And then one last thing before we start to do this math, I just want to remind you while we have this diagram up, sine of theta 1 is equal to x11 divided by the hypotenuse, which is d11, sine. Now, the problem is we cannot take the derivative of this stuff when we're with respect to x10 because everything's in x11 or in the n2 frame. So we got to adjust that. Okay, so we have d11, and we want to convert the inside components to the x1 frame, and we use the same principles as we've defined earlier in this presentation. And then we essentially can pull out n1 from there, right? So n1 squared, we factor it out and do the square root is essentially like this. And kind of the same thing with d22. We can factor out n2, and now we get everything with respect to the main reference frame. And again, we do one more step here. Okay, so those are our two equations, and now we do the derivative of that with respect to x1 or 0, so d. Right, so we have n1 over, remember there's a c component. So we have to do the chain rule here, so the derivative of x1 squared is just 2 x1. And then we do the derivative of the square root, is 1/2, and that gives us plus. We do the chain rule again, but now we have this minus x. And so we get a factor of -1. Right, so then we have 2a1 Again, we have the 1/2. The whole thing is a minus x10 squared plus y20 squared minus 1/2. So if we simplify this, is essentially x10 over minus I put it not sure, I didn't mean to square that. So G20. Now we are going to do the inverse transformation as we did last time. N1 divided by C10, X10 divided by N, 1 over N. Right, and so basically this is, well, that should be a 1, that should be a 1. This is canceling, this is canceling. And now we have basically, this is D22, D1. I made a mistake here. This should also be X1. Right, so X11 over D1 is equal to sine theta 1. And then G22 over the square root of this, over D22 is just sine of theta 2. We also know that C10 is equal to C divided by N1. Right, so N1 squared over C times sine get rid of the C's, and we end up with a new relationship. And this one works. So actually, so with my simulation, it's dependent on path lengths, how small steps you're doing. But basically, I was calculating 1.748 arc seconds, but it rounds. And that can, depend a little bit on the parameters of the simulation. But anyways, what we have learned here is that light appears to slow down in higher densities, and it turns towards increasing n. It also gains more apparent energy in that frame as we go to higher densities. Okay, so let's look at what actually went wrong with our last assumption. So N1, 2. Right, so we have momentum of 1 coming into the boundary, P2's coming out, and we know we have this relationship that still holds. And now we have this new relationship. Which can basically be readjusted. right? So we're solving for P2 equals N1 and so the P1s on the bottom can go away, and 2 here can cancel 1 here, and this one can cancel 1 here. And that leaves us with right, so the parallel components of the light ray are not actually conserved. They're adjusted. They're reduced appropriately as well. Okay, so let's just look over. So we kind of came up with this general idea, but let's look at some of the concerning issues. I'm sure there's more than I really want to know, but we're just going to kind of look at a couple few here. Right, so the first one is special relativity is weird. Essentially, when Einstein did the main calculation, he was saying that a light ray is moving back and forth off some mirrors in a moving frame. However, we cannot we can't actually measure the C here, and that's a big part of his proof. And so what we actually see is a velocity component here, and that whole frame is moving. So light itself is moving in that frame, C1 frame, but relative to our stationary or, zero frame. And it just so happens that Einstein says that this is C. We can then do some geometry here. We know that C10 is just N. We're going to move N over and this stuff down there. So then C squared over and now we're going to do 1, right? So then N squared equals 1 over 1 minus V squared over C squared. And it just so happens that that equals gamma. So if we assume that this diagonal is C, we actually get the right answer. So it's weird, but it recovers itself. So this is a little bit more of a little larger of a weird thing, is that I'm arguing that this whole area is at a higher density. So we're going to have dx1 and dy1, right? And then we're going to have our standard units as dx, dy. And what I'm saying is that dx1 times n so we can normalize the shrinkage of dx1 and dy1 in order to get back to our normal frame. And so we have a light ray bouncing off of 2 mirrors. And, well, maybe we just have one direction here. So if we're looking at the distance traveled from the stationary, well, this is BD. So that'd be the distance in the frame 1, it'd be D, but we're looking at D0. So the distance from our 0 observer. And so the time, T0, right? So the distance traveled is going to be proportional to the velocity times T0. And there's going to be some distance x here. Right, and again, we have D. So this distance that we observe is going to be proportional to n, such like that. Okay, so we're going to try to figure out what x is, and I'm going to make a couple, just, so D, so if V equals 0, this is going to go to 0, right? And we essentially get D, which is going to essentially be the distance 0 covered is going to be the speed of light times T0. Okay, and so now if V equals C, n goes to infinity, and so right, this D, basically D0 is going to get shrunk to 0, and V is going to go to C, and so then we get V and so basically what I'm just arguing here is that x is a really good guess to be equal to this. Our new equation is D0 squared plus I'm sorry if you can hear my dog chewing on a ball in the background, but that's just the way it is. So let's divide through by T0. And we're just going to be looking at this component here. Essentially, that's just D divided by N. And all that to get us right back to where we started from on the previous slide. So ultimately the symmetric contraction in both directions in the x and the y position, not just along the length, is going to result with the same kind of time dilation that we calculated using Einstein's process. Now, one more concerning thing is that the circumferences, as seen from far away, may not agree. Now, in general relativity, as I was saying, I believe that if you have a circumference that you see from a non-distorted frame and you move that into frames that have more stretching, that circumference, this distance here is not going to be accurate, but the circumference is always going to appear to be the same size. Now, with spacetime particles and having an increase in density, you would expect that there would to be a symmetric compression radially and laterally. And so basically what would happen is if you have this ring here and you drop it into, areas with more and more space-time, this ring is actually going to appear to look smaller because there's more distance smashed into this area of higher density. Now that is assuming that the space-time particles are getting distorted symmetrically. You could still have kind of the same thing if it is an asymmetric distortion, where it would only get distorted in one direction, and or we could kind of get a little of both. So I'm still kind of flopping between the answers. One of these solutions, symmetric makes a lot of sense in my mind. However, I think there is probably some sort of asymmetric distortion. So I believe the answer is somewhere in here. And we'll get into that in more detail, hopefully down the road. So what the takeaway here is that the path lengths of light rays and the time delays might not agree. Energy change is still the same. Your photon starting very far away and coming back at very far away is going to be the same in both situations. It's just the path length and maybe the deflection. Well, I guess the deflection is also the same, but it would just be the the path length, the time delay, and how that looks is that's a mass, right? So all the way up here is going to have our and just a little bit of, so the path, the delta path is equal to R plus and your circumference distortions. But when gravity or when the mass is relatively reasonable, this is going to be indistinguishable. However, if we're shooting light around something that maybe is way more aggressive, now our circumference distortion is quite a bit larger. And so I was going to test this, but I wasn't really sure which assumptions were made with the time delays of light paths, so I shelved it for later. But when I'm looking at this later, we'll study this a little bit more. And so this is just a to-do. Now, again, this was a redo of the previous installment here. And so the next step, we do talk about frame dragging. I'm probably going to have to redo that one because I'm not using the exact same math as I defined in this one. But we will get to that. So frame dragging's next. And thanks for your interest. And if you have any comments, please let me hear them below, and like and subscribe, I guess, if you're interested for more. We're doing some pretty interesting stuff here, and I hope you can have an open mind and kind of see where we can go with this. All right. Until next time, thank you.